Okay. Hello, everyone. Welcome to our first ARMA Future Leader Lecture of 2024. I'm pleased to welcome our first speaker of the year, KJ Im, Dr. KJ Im, who's a senior research scientist at Caltech, working broadly in the areas of induced earthquakes and simulation. And so KJ received his PhD from Penn State University under supervision of Derek Ellsworth and Chris Marone. And today he's kindly agreed to give us a talk on simulating earthquake sequences and his recent work looking at discrete fault networks. So with that, thank you, KJ, for offering to give a talk, and please, the floor is yours.
All right, thanks so much, Bing, for invitation. In this talk, I'm gonna introduce an earthquake simulator, induced earthquake simulator. We name it recently. The name is QuakeDFN. It's being developed in the Caltech Industry Cooperative Research Center, which is a GMG. This is one project in the GMG, and we've been developing for a while, and recently, like a beta version is being tested in the GMG, and I'm getting good feedbacks. People think it is fast and easy to use. So I think it is a good time to introduce my simulator. This work is under review in a paper in a journal. So once the journal is published, paper is published, then we're gonna open the code. So this is a QuakeDFN. The DFN is discrete fault network. It's not discrete fracture network, which means we're doing earthquake simulations. So basically, you have discrete faults like this complex fault system, and then if you have an injector, the simulation, and then you can simulate the rupture based on the stress field you apply. And then you can also apply like planar fault system and see some scientific observation that you want to how the earthquake evolves with injection and stuff like that. So we've been developing this for a while. The first version was the 2D version. This one is published last year. The 2D version is not injection-induced earthquake. We try to see how the earthquake interact basically in a complex fault system. So 2D version, as you can see, we have this fault zone and we have distributed fault system in the surroundings. And each fault interact, and we have rate and state friction law. And because of, for example, one fault rupture here, and that stimulate the others. And because of the interaction, the other fault is stimulated. And you sort of have foreshock, a main shock, and aftershock sequence. And this is our simulation result for 2D version. As you can see, there's a main shock and aftershock. But when you have a look at the here, you see there's a foreshock. So we, because it's a simulation, it's good. You can conduct a lot of simulations. So we conducted actually 100 simulations and stacked them. And then we find that we have foreshock and main shock and aftershock. And we have this inverse Omori law and Omori law. So these earthquakes like that follows, and that can replicate what is observed in nature. So we're thinking that this 2D version of QuakeDFN is working very well. So we decided to upgrade it to 3D. And because we're in the GMG, we're basically consider the system, injection-induced earthquake system. So for example, we have, for example, if you have like this complex fault system, this is the fault zone, fault geometry of Prague earthquake in Oklahoma. So you have complex fault system, and you have injection here, and that triggers the earthquake. Foreshock magnitude 5, and the main shock magnitude 5.6 or 5.5 or something like that. That happened like after 1 day from the foreshock, and then you have magnitude 5 aftershock. So the idea is if you have this fault zone, and if you know what the stress field is, so you get the fault zone, fault geometry, and stress field, and then you can put it in the boundary element, three-dimensional boundary element. Because you know the stress field, you can actually calculate what the initial friction or what the initial stress is basically for each bolt based on the orientation. And then you can run the simulation. And this is our formulation. We use rate and state friction, which is modern friction that most of the earthquake simulators are using these days. And Kij, so we have these two stiffness metrics. One is the shear stiffness metrics. You have displacement, and that you calculate what J element displacement influence to ith element. So these boundary elements, boundary elements are like cut it into a smaller piece. So you discretize it further, and one displacement influences the stress to of the others. So that's basically what it is saying, what it is defining. So what the stress transfer is, we're using Okada 92 solution. And then we have this external stress term, which are here and here. And this is the one that you can apply like external stress that you calculate from somewhere else. So it can be a tectonic loading, it can be something else. You can use your in-house like geomechanical simulator. Here in this example, we simply put a spherical pressure diffusion solution, which is an analytic solution when you have an injector and pressure diffuse spherically, and then you calculate the poroelastic stress as well. Called a Rudnicki solution, Rudnicki 86 solution. And then we have this radiation damping term, which is common, which defines the like energy loss from the wave radiation. So basically what it is saying, right-hand side is very widely used quasi-dynamic approximation. This is something that most of the earthquake simulators are using. Not most, but many of the earthquake simulators are using. And then we have this overshoot effect on the left-hand side. And this overshoot effect physically defines the overshoot. So we have this lumped mass term, and it physically defines the overshoot. So it does have been physical meaning, the reason that we put. And also another reason we put it here is to use the method that I presented in my old work in 2017. This is one solver comparison, like spring slider system. And the typical Lungi-Kutta fourth order solution, you have to have very small delta T. If you want to solve rate and state spring slider system, you have to use very small delta T. And the method I use, we can have a much larger delta T. And basically you can solve it much faster. So once you have radiation damping in the system, so this simulator, I didn't put the radiation damping in it. Once you have radiation damping, the gap is not that dramatic, but still ours is much faster, and we can use larger delta T that I find. So we're using this. So I believe this is one of the biggest reasons why my simulator is fast. And so we did the test. So we did the several tests, 3 benchmark tests with the simulator. The first one is a C's BP5QD. This is our earthquake benchmark study. The first reason that we running this simulation is to see what the overshoot effect influences, and to see if our simulator actually works similarly to the widely used quasi-dynamic approximation. So the geometry looks like this. We have a loading. Loading is applied to the fault, and we have a loading fault in the surrounding. That I don't have loading fault displayed here because that one is super large. And velocity strengthening area, and then we have a velocity weakening area. And there's a slightly more unstable zone here. And this is our simulation result. You have nucleation here, as you can see, and then propagation, and then interseismic period. And we compare our results with one of the solution in Z's study benchmark solutions, which is the red dash line. This is the simulator with USC Sylvan Babut's simulator. And our simulator is these different colors. We have M term that defines the overshoot effect. So we use a wide range of M term. If M term is large, as you can see, we have overshoot. So the benchmark solution and ours has a little gap, and this gets larger because we have overshoot basically. So this term defines the overshoot. So when the M term gets smaller, you actually see that the overshoot effect gets smaller and smaller, and at some point it converges to values somewhere very similar to BP5QD solution. So what it's saying is this M term defines the overshoot effect, which is physical. And as you get M term smaller and smaller, you actually converges to the benchmark solution. So that's exactly what we were trying to see. We actually have a method to define this M term, and this blue is something that we typically put in the geometry fault system like this, and then this blue is something that we're typically put in our simulator. So this is one benchmark test. Yeah, I think one of the things that we're showing here is that this simulator is similar to a widely used quasi-dynamic approximation, which means it's different from another like well-known simulator, which is what is it? RSQ sim. So the RSQ sim is actually doing something similar that I'm presenting here, but they use different approximation. They're not using this. They use stage-based. They call it state-based approximation. They use different different governing equation basically, but we don't have that. We use our simulator is very similar to what people are typically using. And then because our simulator is basically discrete fault simulator, so we tested we try to compare our simulator to some benchmark discrete fault solution, and this is one example in the compression step over. It's a recent paper in Kyra Kroll 2023. They use these two fault system, two parallel discrete fault system, which has a little bit of overshoot, and there's a nucleation region, and the earthquake propagate, and that jumps to the other fault, and see what's going to happen. So in our simulator, we define the friction change at 0.49 to 0.38. The initial shear stress is uniform in the system, and then there are two benchmark simulator. One is a fault mode, and the other one is RSQ. Fault mode is fully dynamic finite element method with the slip weakening law. So it's different from our method. And RSQ sim is a quasi-dynamic boundary elements method, which is similar to ours. They use rate and state friction law, but they use a state-based or stage-based rate and state friction law. And then they have to have an inherently discrete grid. So we're using same method of same rate and states boundary element, but the approximation method is a little different. And this is our simulation result. What you're seeing here is the velocity, the nucleate, and it jumps to the other fault, and there's a back propagation into the main shock fault. And we're setting the friction change, like friction drop, identical to the other, similar. We cannot exactly define the friction drop because it's a rate and state friction, but like tuning A, B, D sub C parameters, we get the friction change of 0.49, 0.38, roughly similar to what they have. So we expect at least the displacement to be the same, similar. And this is our simulation result of the displacement. So this is exactly the same simulation result that what you're seeing here is the sleep displacements on each fault. And as you can see, this is our KTFN results, and this is fault mode, and this is RSQSIM. So when you have a look at this color code, you see that they are more or less similar. So yeah, we can actually get the similar. I'm sorry, I have something here. I keep having it. There's displacement distribution is basically similar. For RSQSIM has a little noise here, but overall your displacement is very similar. And then everything nucleate and propagate, and ours propagation is a little slower than the fully dynamic simulation. And the RSQSIM looks like it is the fastest, and the fully dynamics is slower, and ours is the slowest. But if you use the quasi-dynamic approximation with the radiation damping, it's very typical your propagation is slower than the fault mode, than the fully dynamic simulation. So at least we'll get the same stress drop, displacement, magnitude of stress drop or displacement, and we're satisfied with the benchmark test 2. So we move on to the benchmark test 3. We try to benchmark with simulation results with branching fault and also like depth-dependent stress field. And then we found this, and this is USGS called the verification project, and this is also a fault mode, fully dynamic slip weakening node. They have this branching fault. You have a main shock fault, and then you have a smaller branching fault here. Similarly, you have nucleation and propagation. One difference is from the previous example is that the stress is now depth dependent. So, and then stress is applied basically as a tensor here. So this branching fault has a smaller stress. As you can see, this is much red, and this is a yellowish, which means the stress is lower because you're applying the stress field, stress tensor here. And this is our simulation result. So you expect a larger stress drop in the deeper area, a smaller stress drop in the shallow area. And this is our simulation result. So when you everything nucleates here and propagate, and as you can see, deeper area displacement is larger because stress drop is larger. Stress is depth dependent in this case. And also you can see that as this main shock rupture passing this branching point, you see that displacement decreases at this point because of this competition between these two. The stress drop or friction drop is basically separated into these two folds. That's why you have sleep decreases at this point. And we'll see if our simulator later can pick that up. And this is the simulation result. We don't have the slip distribution of our benchmark solution. We only have like point displacement, and we compare our displacement and these points to the fault mode, and we find that they are more or less pretty similar. There are some differences, especially like timing of the rupture. Our shallow rupture occurs much earlier, and it's basically because of it's a quasi-dynamic solution. The stress change is basically instantaneous. So you have displacement change the stress everywhere. That's why the rupture timing is similar. It's a little different. But once you can see that the magnitude of displacement is more or less similar. So we was satisfied with the benchmark test 3. So we tested if our simulator corresponds to widely used simulator, yes. And fault jump, yes. And a branching fault with depth dependent stress, yes. So we think it is working well. So now we move on to the injection-induced earthquake simulation. Yeah, in this case, we use this external stress term, like I said. we use this external stress term as a pressure diffusion solution. So you can calculate if you have a fault, and if you have a injector pressure injector, you can actually calculate what the shear and normal stress change and pressure change according to the Lagrange solution. So it will give you the stress tensor and the pressure, and because you know your fault orientation of each element, and you can rotate the stress tensor to along with your fault element, and calculate the stress normal and shear stress change. That's basically what we're doing here. And then you can put the normal and shear stress change here. And we run the simulation, and the simulation result looks like this. You have injector here, you initially have smaller rupture, and then it gets larger and larger. And we put like running solution here, and basically you can put any geomechanical, other like tonal geomechanical simulator or tectonic loading here. And we have this strategy. So you have complex fault system, you apply a stress, and then you can calculate the initial friction. You can roughly measure the friction parameters. Of course, it can be like very precise along the whole point of the fault, but you can roughly measure the friction parameters. You can relatively better estimate the rock properties, and then you can roughly estimate the stress field. But the good thing is that the simulator, you can test actually a wide range of these guys and do the simulation. So we define these first, and then we use the spherical poroelastic stress change that I mentioned, running solution. And then there are two parameters that is not defined. One is the initial velocity, and one is initial theta. And when you have a look at the evolution law in the right-hand state friction, when the velocity is very small, maximum d theta over dt is 1, which means the maximum theta is the time from the last rupture. So we define theta first, and then decide the v correspondingly. So that's our strategy. We use different fault geometry. One is planar fault, and the other one is interacting two fault, and then the last one is complex fault system that we adopted from Oklahoma Prague earthquake. Before we get to the planar fault simulation, I want to talk a little bit about rupture mechanics. In 2012, Garagash and Jovanovich discussed that when your initial friction is smaller than your residual friction, so once you have a rupture, you have a residual friction. If initial friction is lower than the residual friction, you have confined rupture, the rupture arrest. And if initial friction is larger than the residual friction, and you have like a runaway rupture. So you can estimate mu r this way, like steady state friction at the rupture peak velocity. And then you can have the mu I minus mu r this way. So it's a simple calculation. And then you see that we define this as a runaway potential. And then you can see that this runaway potential is only dependent on initial velocity and initial theta, other than the friction parameters. So if you have if this term is large, you have higher runaway potential. And then if this term actually become positive, you have good chance that the earthquake will run away. If this term is negative and it gets smaller and smaller, you have confined rupture. So we adjust the initial velocity and initial theta and run the simulation. We actually ran 24 simulation with the different initial velocities and initial theta values. We have a little bit of a heterogeneity of A minus B values. So you have a unstable area in the center and stable area in the surroundings. And the normal stress is depth dependence now. And this is one simulation result. So where this runaway rupture is the lowest, so we expect that the earthquake will be confined rupture. and it's self-arrested. As you can see, you have small rupture, it's arrested, and it actually gets to become larger and larger. So because it's a self-arrested, maybe many people will think it is a induced earthquake. And as you can see, the magnitude gets gets larger and larger as time goes by. So this x-axis is a day. Then you can also say it's an injection volume, because we're injecting at the constant flow rate. As you can see, the magnitude gets larger and larger, and the epicenter is, as you can see, the epicenter is here. So it gets away. See here, here, here. It gets away from your injection center, which is very similar to typically what is observed when you do the injection in the induced earthquake. Now, next one is this case with the runaway potential. It's still negative. Okay, runaway potential is still negative. You still have this confined rupture. We are still in the induced earthquake regime, and the magnitude increases. Distance from the epicenter goes away from the injected, which is basically very similar to the other simulation results. And now we move on to the area where this positive runaway potential, which is red here, which is this here. Now you're injecting here, you have a little small event, and then at some point, it gets to run away. You cannot stop it. It goes all the way to the boundary of the velocity weakening and strengthening boundary. And the next case is our largest runaway rupture case. As soon as you inject, it gets to run away, and then you cannot arrest it. And then the inside resets. Somehow, okay, you get that runaway rupture, and inside here, the friction resets, and then your earthquake size increases with time as well. So, like I said, we conducted 24 simulations basically. This is y-axis here is a magnitude, and x-axis is injection volume or time. And now we put it in the log scale. So, and then each color code represents different runaway potential. So each color code represents each simulation. So if it is red here, it's one simulation. The blue, one simulation. This orange is one simulation. So we have 24 simulations. As you can see, if you are in the runaway potential negative regime, their maximum magnitude tends to line up like here. The blue ones, these blue ones, runaway potential is low. They tends to line up here, and runaway potential is large. They tends to stay somewhere here. So if I connect the maximum magnitude event, so some of the blue ones will be here, and some of the orange ones will be here. The yellow one may be something like this. But if you're only connecting the maximum magnitude event, you see that there are some regime change. You initially have line up here. If your runaway potential gets larger and larger, it shifts to some value. Now we put the McGar's 2014 example here, but somehow it looks quite somewhere along this, when it's touching this McGar's prediction, is somehow it just started to be in the regime of runaway rupture regime, and then you get this curve, and then your runaway rupture, and then injection volume. So this is the plot of this point of injection volume y-axis, and injection volume of when it reaches to magnitude 4 increases as your runaway potential decreases. That's exactly what we're seeing here. But there's some point that it turns into self-arrested induced earthquake to trigger the earthquakes. And this curve looks very similar to what you typically observe in nature. In nature, you have if you, based on your initial states, you have injection volume, you sort of have this low linear straight curve. You actually have many of this low linear straight curve. They're mostly under the McGaugh's predictions, but somehow you sometimes have like this, some small earthquake, and then goes through on a rate rupture. Is basically what we're seeing here. This is a Pohang example, but most of the other cases it stays on the here in the region where the induced earthquake region. So our simulator can reproduce this maximum magnitude prediction observations in nature. Now we tested the branching fault system, which to see if our simulator works as it is designed. For example, if you have like different stress orientation and different fault orientation, and see if they're working correctly, pick up that orientation effect. So now we have different stress orientation and the two different fault angles. So we have two branching fault system. One is 90 degree and the other one is 60 degree. And then we varies this the maximum stress angle from minus 75 to 75. And then we also try to look at the runaway potential. So the runaway potential is basically initial friction minus residual friction. So if you calculate it, this is the formulation that I showed in the previous page, but it can also be represented in this way, which means that if mu gets larger, because mu I is calculated from the stress field and fault orientation, if mu gets larger, the runaway potential becomes smaller. So if your mu is smaller, which means your available stress is larger. So if mu is smaller, runaway potential gets larger, the system becomes unstable. So this is one example. When you have when you apply this, I guess is the example of this case. You have this two-fault system. You have a stress orientation is -30, which means it's a 30-degree angle here, 30-degree angle here. Then you will expect that their initial velocity, they're more likely critically stressed. So based on the rate and states, you can set up the initial stress velocity, and you see their initial velocity is pretty high, relatively high here. But if you are here, positive 15 degree, this one will be very stable, and this one will be relatively still like a little stable here. As you can see, that's this fault initial velocity is low, and this fault initial velocity is lower. So this is how we set the simulation. Just so based on your stress orientation and fault angle, you can calculate the initial velocity with the strategy that I presented in the previous page. So with that in mind, and this is our simulation results. So the x-axis, what you're seeing is a stress orientation that we tested here. -75 is here, -60 here, -45 is here. And this is the case for 90 degree. And this is the case for 60 degree. Now you have -75, -45, 36, 15. That's what it is. And the y-axis is mu0. I said when the mu0 gets higher, your runaway potential decreases. When the mu0 gets lower, your runaway potential increases. So if you're here, so if the y-axis is smaller, you will expect larger earthquake. That's exactly what we're seeing right here. When the mu0 is smaller, you tend to have large instruments. So the blue one is the maximum earthquake of this blue fault, and red circles represent the maximum earthquake of this red circle. So they actually happen at the same time. So, but I separated their seismic moment intentionally to see what their magnitude is. And then you can actually calculate where the system become runaway. And if you calculate it, you like mu I minus mu0 to runaway, equals to 0. This is not exactly the point where it starts to run away, but it's an estimation. So you can actually estimate where the runaway potential becomes 0. And if it is under it, you actually expect that the system will become unstable. And that's exactly what we're seeing. The red fault, because we're doing injection here, it will rupture until even your mu0 is very high. But the blue one, because you're not injecting on it, only ruptures when their runaway potential is larger than 1 in this case. And we try to see. So basically, we find that the simulation is working as it is designed. It works as what mu0 is. That's exactly what we expected. So it pick up the stress field, stress, and the mu0 effect, runaway effect. And then when we have a look at these two cases, so it looks very symmetric, because because it's a 90 degree. So if your stress field is here and its maximum stress is here and here, in terms of maximum magnitude, they are symmetric. But when you have a look at the velocity rupture sequence, you see that there are a little difference. For example, when you're here, so your maximum magnitude, maximum stress field orientation is -45, which is this angle. And then you're injecting here. And because of this stress angle, this red fault will be right lateral. And then you can intuitively think that here, normal stress will be decreased. The rupture may propagate this way. And that's exactly what we're seeing here. Okay, and the rupture propagates south first, and it goes to the north. But in the other case, although they are symmetric, they're different because in this case, the maximum stress orientation is 45 here, and this fault is left lateral. Now normal stress decreases here, so you would expect this earthquake trigger the other earthquake, and it will propagate north first, and that's exactly what we're seeing. So it goes north first, and it goes back to the south, just like what is predicted. So, and then there's one interesting another interesting case, that in the case where the angle is -30, which means this fault is very optimally oriented for a rupture, and this fault is not quite optimally oriented. And in this case, as you can see, there's no red circle, it's only blue circle. And what happens here is that you have aseismic nucleation, and that triggers the earthquake in the main shock, main shock fault. You have aseismic sleep, and that triggers the earthquake. So in this branching fault system test, we find that the simulator actually works as it is designed. So we move on to do the complex fault system. So this is the system with a Prague earthquake in Oklahoma. You have complex fault system, you have an injector, and the faults interact and see what's going to happen. Basically, because it's the earthquake simulator, you can test wide range of the parameter space. So we use 3 different angle, sigma 1, maximum stress angle, and that defines the initial loss, initial friction. And then we also tested different criticality of the fault, or different runaway potential of the fault by adjusting mu0 here. And then we tested different data value, and the initial velocity is automatically calculated based on these assumptions, and then you can do the simulation. And if you do the simulation, we conducted 36 simulation. These are all the 36 simulation. What you're seeing here is maximum magnitude of the earthquake. And these are all the simulation results. The faults are more or less critically stressed in this case, and our injection rate is very low. because that's what it is in actual field. Their injection rate is very low, and the earthquake actually occurs after like 20 years of the injection. And these are all the simulation results. If mu zero gets smaller, which means the runaway potential increases. Mu zero gets larger, runaway potential gets smaller. So your system is stable here and unstable here. That's exactly what we're seeing. And stress angle actually influences the rupture magnitude. And also the theta influences rupture magnitude as well. When you have a look at this line, this F line, so we zoom in that, and when you have a look at this case, so if your mu zero is a small, your runaway potential is very large. This is the simulation. So when you inject water, once it triggers the earthquake at the day 192, so every fault ruptures altogether because the system is very unstable. And in this case, where here mu zero is relatively larger, means your runaway potential is still also relatively it's a runaway potential is relatively smaller. In this case, when you conduct the injection, the rupture propagate and trigger the main shock, but it doesn't trigger the ones up here as you see that it triggers everything. But this one is a little confined, this foreshock and aftershock fault. But the last case is this: if your mu zero gets larger than a certain value, then your earthquake, this foreshock doesn't trigger the main shock rupture. So this is the case. So there are some gap, but in reality, what you actually see is that you have a foreshock, this fault ruptures, and that there's 1 day gap, and that triggers the main shock. And we would like to reproduce that. This simulation is basically not to try to precisely reproduce the earthquake sequence in Prague, but we still want to see that. We still want to see. So this is the case, the foreshock and aftershock ruptures are together. So it's only one earthquake rupture. And this is the case, only foreshock ruptures. So if we dig into somewhere in between these two, maybe we can have something like this. So we adjust the parameter, and somewhere here, mu zero is something somewhere in between. I think it is a 0.3155 something. And then you actually see that the main shock there's a foreshock ruptures, and there's a small gap, and then the main shock rupture. So this foreshock rupture and main shock rupture in this case has 1 day difference, as exactly observed in the actual field. So what we find here is that our simulation is stable in complex earthquake rupture system. So here's the conclusion. I would like to say here is, I don't know why it's not moving, it's not showing. I'd like to say that it's efficient earthquake simulator applicable complex fault system, and we benchmarked, and we think it is successfully benchmarked, and it produces realistic earthquake sequence based on the local stress field. And the paper is under review. Once it's published, the code will be like source. I think we're gonna open the source code to the public, on the GitHub. All right, that's the end of my talk. Thanks so much.
Thanks, KJ. This is really excellent.
All right, thank you.
I'm trying to do the applause emoji too. There. This is all in one paper.
Yeah, it's just all in one paper. Some of the works in I don't know. Yeah, it's all in one paper. Yeah.
Derek Ellsworth says, "Nice talk, KJ, and nice work. Well done."
Thanks, Derek.
Please, everyone, if you have questions or comments, either leave it in chat or feel free to unmute yourself.
Yes.
Happy to have a discussion.
Happy to answer.
Okay, so I can read it for you if you'd like. Guo Tianyang at Stanford asks, nice talk. How do you get the magnitude of the induced earthquake from the velocity in your model? Um, he did attend late, but I'm sure the audience would appreciate if you
Yeah,
elaborate on that a little bit.
I guess if you're like some technical side of get the seismic moment.
Yeah.
What we do here is because we have this element, we gather based on our criteria, we gather the information of each element, rupture time, and seismic moment. And align with time, we have to apply some criteria. Like, for example, 1 second is criteria. We go back to 1 second for each line, each element. And if there is an event within 1 second, within some distance, we merge them. So if you're an earthquake, for example, you have rupture here. So you have this each element. And if any of the previous event is within the criteria time, within the criteria distance, we merge them. Their seismic moment is merged, and then it's shown as one event. That's how I calculate the earthquake magnitude here in this work.
So potentially, if the magnitudes get really large, this 1 second might need to be adjusted.
It's a 1 second, but like if it is, for example, it merges. If 1 second within 1 second, if there's an event, the same within this within 1 second, within, for example, 1 kilometer or 500 meters, if one element ruptured, and then I track everything, the merged things before it, and I merged all the time, everything. So this event and this event doesn't necessarily has to be within 1 second. If any of this event and this event is within 1 second, I merged everything. So that's how you calculate magnitude in this work.
Oh, excellent.
So you have
do we
this
have
event.
other?
Yeah.
Okay. Did we have other? Guo Tianyang says thanks.
All right, thank you.
Are there any other questions from the audience?
Okay,
Hi,
nice talk. You showed some plots where the trajectories went parallel to the Magar line and some that went across. What are the criteria that allows it to transit that line or stay below it?
We're actually working on it with fracture mechanics. I guess Alexis here. I'm reading his papers. I find that what the rupture length, how the rupture length evolves theoretically, and this Magar line, it somehow in this example or some of my other examples somehow stays here, but I'm not really sure if there's like this is one example that I ran it, so I don't have theoretical expression for why, I'm not really sure if it is a Magar line is actually it or some other criteria we can create it, we can generate. But
Well,
this is just one like to show you that what's the magnitude that we're seeing here to compare our results with the observation in my guideline as well.
So what are the actual trajectories for a bunch of different simulations? Because you think you'd have a point, right, rather than a line.
Yeah, the point of these earthquakes, and I just connect the maximum magnitude. So some of the blue will start here, and then you connect the maximum magnitude.
Okay, gotcha.
And that's what it is. Yeah.
Great. Thank you.
Thank you. Thank you. Good to see you, by the way.
Likewise.
Okay. Other questions from our audience? Okay, I do have a few. I'll start with the first one since we're on this slide. Could we think of this mu naught as an analog for maturity or for sort of the state of the fault? Is that
it's a rate and state parameter. So mu naught is like
right?
when you have a look at the rate and state, it's I think the biggest it's most strongly dependent on the minerals. So if you're most of the time when you have large like granites have larger mu zero and shales have lower mu zero. I don't know if it can be you can define as a maturity or I don't know.
Okay.
But that's what
Interesting.
it's a rate and state parameters. It's basically something you can measure, but it's you know, the friction measurement is not very straightforward always.
As you're very familiar with. You show that slide where you have the Prague earthquake, and you plot it on your on your mu zero plot, like close to the end.
For example, here.
One more. I think you want.
Oops. There's some delay here.
Oh,
okay.
I see. One more. You show the where the progress earthquake plots on the mu zero. Yeah, this one. So does that count as a relatively high value then? With that, like if we plot, for example, like Southern California faults, would that plot much more? Where would that plot relative to this one?
This mu zero?
Yeah.
I don't know. It's
okay.
It probably is a relatively large for example, like unstable faults. But they are typically like by a Reed's law, they say 0.6 is something typically want to put like I say, I'm not trying to precisely reproduce Prague earthquake.
Yeah,
I put try to see what happens when you put the stress field and then see that's to see if my simulator works well, and that's
okay. No, it's impressive that you get the roughly the right time interval and that the second one is a bigger magnitude. No, this
yes.
That's really cool that you can get that. Matteo, you had a question.
Yeah, hi everyone, and thanks for the organization. Great talk, KJ. So I had a question. You're showing that the runaway potential depends only on the initial velocity mainly, right?
Yes.
The theoretical analysis of you know, whether a fault runs away or accelerates towards instability would tell you that the potency of the injection also has something to do with it, and you should be comparing. In theory, you compare the stress criticality with the potency of injection. And for sleep weakening faults, it should also be the fracture energy that intervenes there. So do you have any idea on how to reconcile these two observations where you only need the initial velocity here, but for other theoretical analysis on sleep weakening faults, for example, it's very different?
We're actually I'm actually looking at it based on the Alexis work. I'm looking at my like rupture length. Actually, is pretty well predicted by Alexis work, the length of the rupture, and Alexis work actually have fluid injection rate influences and stuff like that. So I'm digging into it now, but I don't have a firm idea about it.
Okay.
Yet. Alexis, you have any comments?
Yeah, maybe I have one comment on that for Mateo, that so the stability condition of running away or not, actually it's interesting, but it doesn't depend on the fluid injection itself. So at least theoretically,
Okay.
depends on on the sign of the difference between the shear stress that is before, like background shear stress on the fault, and how it weakens basically your frictional resistance on the fault towards the residual value. So this is on top or below or above this initial stress. That's and then the analog of that is what KJ I think is doing with the in the rate and state framework, like translating from slip weakening to rate and state. So that condition you can show in by energy considerations that you get this kind of behavior. Does not depend basically on the fluid injection.
Okay. Okay. Thanks.
Very cool. Okay. Other questions from the audience? Whether by chat or please unmute yourself. Okay. In that case, thank you again, KJ. I'm going to stop.
All right, thank you.
This is excellent and really interesting work.